great information. And this hopefully will dovetail with quite a bit of it. This is on what we're doing with hyperbaric oxygen, pressure oxygen, and gene therapy. And I'm going to give you a slide here at the end that I am hoping you will start to use to talk about what we are doing with other physicians and the way we need to characterize this therapy. Okay, I want to review again, and this is getting boring for some of you, but I just don't think we can say this enough times. We need to firmly understand what hyperbaric oxygen therapy is about and get away from the misinformation that's been a part, at least, of hyperbaric medicine for my generation of doctors. So if we just ask the simple question, what's hyperbaric oxygen? We've seen this many times, this definition. And of course, we've seen the list of diagnoses that go with it, which as a group is a very disjointed group that seems to have no connection. I mean, chronic bone infection, radiation damage, burns, brain abscess, which is actually 3 conditions. Parenchymal abscess, subdural empyema, and epidural empyema. And all distinct entities. And the approval, if you will, or to get on this list, was 13 published cases. 13 published cases. And 6 that were unofficially reported in a yearly call-out from, I believe, 92 to 95 at an annual scientific meeting. Anybody with a brain abscess that they treated, please submit your case. So there were 6 additional cases comprising 19, and that formed the basis, the scientific basis. Now, does it work for this? Yes, it does. It's adjunctive, it's helpful, and so on, but really there wasn't clinical evidence for it. But again, how do you understand it in relation to the rest of these diagnoses? It's very difficult, and I've always asked the question, can you connect the dots? The average physician, the average person, nobody can connect the dots. The only ones who can connect the dots are the lay public. Oh yeah, wait a minute, lack of oxygen there. Now we're giving oxygen. Yeah, but where's the problem? Well, the medical profession doesn't seem to get that because we've always thought that oxygen is a metabolic substrate. You give it, it's used, then it's gone. So if we expose somebody to oxygen, give them a big blast, how long does it hang around? Well, depending on the tissue and the blood flow, maybe a short time, minutes to soft tissue, hours. Bone, maybe even much longer. We're now finding in a mouse experiment, 24 hours or more, 48 hours. So, you know, the medical profession said, well, we can't understand if you give it, it goes away. How do you get these effects? Well, the newest accepted indication, if you will, is that one. Okay, now, I have to admit, do you know how many randomized trials this is based on? 7. Where's it been all these years? And this has been accumulating over time, but there's 7 randomized trials supporting this. And finally, the National Ear, Nose, and Throat Society put out a position paper where they were reviewing therapies and guidelines for various diagnoses, and this came up as a viable option. They actually recommended it as something to try. Well, it turns out when you compare the evidence to all of the other treatments for acute sensory neural hearing loss, it's superior. So I'll ask again, can you connect the latest dot? You know, idiopathic sensory neural hearing loss is the latest dot on the typically reimbursed indications list, and that comprises all sorts of causes of it. So we have viral causes, traumatic causes, a variety of different things to do with ischemic causes, and it can be damage to the end organ or parts that supply it. So we have a lot of different etiologies and so on, but despite all of that, if you apply hyperbaric oxygen, the preponderance of evidence is you can improve it regardless of cause. But nobody can connect the dots. And it turns out it's the underlying pathophysiology. I turned it off, okay. And it led to the classic critical article that people trumped out for decades. You know, hyperbaric oxygen therapy, a therapy in search of a disease. For only one disorder, decompression sicknesses, they accepted clinical trials which demonstrate efficacy. Guess what? There's never been a randomized trial of hyperbaric oxygen for decompression sickness. There are none. There's one now, I think, in with lidocaine use. But for compression versus no compression, there has never been a randomized trial. That's the signature diagnosis of this specialty. HBO is used to decrease intravascular bubble size. Well, let me tell you. All the animal experiments show that the bubbles go through the brain within 5 minutes. At least all of them less than 5,000 microns in size. So microscopic bubbles, 19 to 21 to 40, 50 microns are passing through the brain within 5 minutes. By the time the US Navy and everybody else gets to it, we ain't treating bubbles. We're treating reperfusion injury, underlying pathophysiology. So, as it turns out, in 1996, the Russians, or 86, the Russians were also doing this. They started talking about oxygen in terms of pharmacologic terms, all of the drug terms and dosing. And this was Dr. Sheldon Gottlieb, who wrote this chapter in the Davidson Hunt textbook in 86. And, it led to us putting this definition out, use of greater than atmospheric pressure oxygen as a drug to treat basic disease processes, states, and their diseases, and while it acts like a drug in principle, not in reality, because it's both a drug and device. And so it led to really a reappraisal. What are we doing? Well, it is the basis of this is the physiology and biology, at least I thought, of intermittent hyperoxia. So if I have a 911 event right now and maybe I get revived or not, I'm going to get 100% oxygen on me, and at some point, shot, we establish circulation, I'm going to stay on 100% oxygen, we get over to the hospital, and who knows how long I'm going to be on, 12 hours maybe, or more in the ICU, if you don't have pulmonary damage. Will you get any of the hyperbaric oxygen physiologic effects that we see and have documented with that exposure to 188 oxygen for 12 hours? The answer is no. So it is intermittent. You have to apply it and withdraw it, which gets to the whole signaling concept. Well, of course, part of the drug principles are one of the most important things is the timing of the dose with respect to evolving pathology. And that goes to much of the discussion today. We were talking about, one lady here asked a question about resuscitation of a newborn with a hypoxic ischemic event at birth. Oh my God, yes. That is the absolute best time to intervene. There's a review article out of China, and I believe Dr. Marwa referenced that. He said about 30 minutes, it's somewhere in there. Articles that have been done applying hyperbaric oxygen therapy in the acute ischemia period for neonates. And almost every one of them has positive result. And then, of course, it all got criticized, well, that was the Chinese literature, it wasn't as rigorous, and they didn't do this, that, whatever. The reality is the same. I mean, a lot of exposure to this, and putting the cases together and publishing it because the effect was so profound. Well, we can go to The Lancet in 1985. No, 65. 65 infants, Hutchison, who were born and failed resuscitation for respiratory failure. So this was term babies born, and they couldn't get them started up. They put them in a little chamber. You can have to see the article and the picture. It's a tiny incubator-like chamber. Some of them were intubated, so there was no hands-on CPR, nothing in there. They just said, okay, that's it, we failed. Put them in the chamber, turn it up to 2 atmospheres. If they didn't start breathing, they turned it to 4. At the end of the day, 54% of these babies were discharged from the hospital, quote, apparently well. Lancet, it's 1965. So the whole point is, where are we intervening in the process and what is the pathology at that point? Well, so the key is to try to dose it by identifying the targets if we can, and appropriately intervening at whatever time that's appropriate to the targets you're treating. And the different targets, in fact, respond to different doses of hyperbaric oxygen. We see that with reperfusion injury. The whole white blood cell inhibition, you have to start hyperbaric oxygen within 90 minutes of the cessation of ischemia. So once you've returned blood flow, you've got a 90-minute clock to really inhibit that reperfusion injury. As it turns out, though, if you look at the study that was done by Zamboni, and it was quoted up here by a number of the previous lecturers, even if you got to it later, you are still beneficially affecting the pathology. We just don't know what the target is. But the outcome was good. So the challenge really is what everyone likes to talk about, personalized medicine. It's finding the right dose for a given patient and that patient's diagnosis. And what did Dr. Neubauer constantly say, right up to the time of his death? You know, well, we really don't know the dose. and every time we would talk about a different diagnosis and share cases and all. And the reality is, if we were 100 and some neurological cases here, we maybe all be, but as we get older, you know, what is the dose to treat each of us individually? We do not have a dosing tool that can assess that. You've seen all the spectrum imaging we've done for many years. That gives us an answer for the dose we put that patient in the chamber for. But if you want to assess another dose, we got to do another dive with a repeat scan. So we get information as many times as we want to look at it. But it's the dose that we pick based on literature, experience, and so on. And in fact, it may be a very wide range, less than maybe 2 atmospheres for chronic injury. So, personalized medicine, you know how this works, universal gas law, Henry's law, amount of oxygen, we could say nitrogen, everything. In solution is proportional to the partial pressure of it. So, you know, gas interfacing with a liquid, double the pressure, double the amount of solution, right? And it's the dissolved component. We always thought of oxygen. If we're looking at breathing air, we got a little bit at just 1 atmosphere dissolved. We got more oxygen at 3 atmospheres, but if we got 100% O2, we got a lot. That exceeds the extraction fraction of every one of our vital organs, which led to the life without blood experiment in 1960. The lead-off article on the cover of Journal of Cardiovascular Research, Borema in the Netherlands took the pigs, put them in a chamber, 3 atmospheres, exchanged, transfused the blood with normal saline. Pigs were alive and fine, retransfused the blood and brought them out. Don't need the blood. And that's what started all the blue baby operations with hyperbaric oxygen, the advent to the United States, the big chambers, and then you saw all the literature in those first few years, you know, the 60s and early 70s. That's what gave rise to it. So, but the question is, well, so if we raise the oxygen, we're just going to fix on oxygen for a minute, how high do we have to go? And do we have to get there abruptly? Is it better to compress on air where you're getting oxygen and air, then you suddenly put on 100% oxygen by a mask or a hood? Or is it better that you have a buildup in a monoplate chamber trying to give 100% oxygen and eventually get there, 15 minutes into it, to 95% or more? And then how long do you stay there? Is an air break good? Do you need 20 minutes? Do you need 40 minutes? Do we need 90 minutes? These are all questions that have not been answered over time. But see, people have applied so many different doses over the years. If you go back and you start looking, you can get some idea for some of this information. And then, what is it that is finally causing the effect? Is it how long you stay in pressure, or is it the habituation, if you will, or adaptation of the organism to whatever you expose them to, pressurized air or oxygen or whatever level, and then the withdrawal of it? Is it the withdrawal that's the signal? Well, we don't really know, but I want to show you something here. This is a veteran in a severe motor vehicle accident. So he's got traumatic brain injury, in a coma, the whole thing, and now we're years out. It turns out he is very, very sensitive, and these are sagittal views, so and I stretch them out a little bit so they'd be on the whole screen and so on, and you'll get the effect. And you can see, and this is SPECT brain imaging, and we were trying to find the dose for him. He is very, very sensitive. He had had some previous hyperbaric oxygen. I wasn't really sure. Where are we going to start with this guy? And so I thought, well, let's try very low and very short. So this is 1.25 ATA for 30 minutes. Now 30 minutes, if we look at the work that Bill Delp has done, and then Lynn Weaver with chambers and 70 kilogram saline bags in a chamber, measuring the PO2 right at about mouth level or so, to see how long the chamber is building up in a standard Seacrest chamber. It's about 15 minutes, 12 minutes, somewhere in there before we're getting up to 95% oxygen. So look at this. 30 minutes, that's compression and decompression time and time at depth. We maybe got to 98% oxygen for a short period of time, and then we started bringing him out with 100% oxygen. Here's his baseline scan, and you can see the heterogeneity of this with the bright areas and this blotchy type of irregularity. Look at this whole left frontal lobe is significantly, and parietal lobe, excuse me. And you can see it throughout. And here is the average number of counts per pixel, the maximum for that slice, total number in the whole slice. And here he is after one hyperbaric treatment at 1.25 ATA for 30 minutes. Is there a difference? Can you see it? It's a smoothing to a more normal pattern. Now we shifted some things around, but this pattern shift corresponds to a more normal pattern. And guess what? He felt better. Surprise. Brain more in balance, working better. I submitted this into a letter. They didn't want it because it doesn't belong in a letter to the editor. But the whole point was, look, we've got lower pressures and doses that can be affected. Well, of course, when we look at this, hyperbaric oxygen as a drug, we've got acute and chronic trophic effects on acute and chronic disease pathophysiology. And you've seen all these. I'm just going to blow through them just to show you. There's a bunch of lists, all the things it can do: inhibit alpha toxin, bacteriostasis, cerebral edema, burn shock, blah, blah, blah. And we keep going. There are a lot of acute effects. Inhibition of reperfusion injury. There are now dozens and dozens of studies showing this. Every organ system, almost every model, all sorts of different animal species. We are way down in the phylogenetic spectrum here of what we are treating. These are basic disease processes that span living organisms. That's why we have a veterinary hyperbaric association these days. And the chronic effects. What are we doing here? We're growing new tissue. Bone, skin, blood vessels, and this goes back to something that was talked about earlier with stem cells. Are we doing stem cells and the pressure you need in the brain? If you go to the article that we published in Brain Research in 2007 on the animal model, which looked at the number of treatments, blood vessel density, and so on. In fact, there was a paper published in Animals that showed that when you develop new blood vessels in the brain, the stem cell from which it sprouts cleaves to give a vascular cell and a neuron. So these are likely in situ cells there. They don't necessarily have to come from the bone marrow. You may be generating and have stem cells right in the brain there that are the issue. But this is what we're going to focus on right here. Ischemic tissue oxygen capacitance. And of course the angiogenesis, just to go through this, the radiation beam model for head and neck radiation necrosis by Marks, which showed that if you take a cross-section of the jaw, where the external beam has irradiated for head and neck cancer, right in the center of it is going to be the densest damage to tissue, loss of blood vessels, oxygen gradient due to that loss, single hyperbaric treatment, steepen the gradient. Everybody thought steepen the gradient, that's what does it. Maybe, that's probably the signal, but there may be other things involved. And as you keep going with treatments, we grow new blood vessels in, and on a long-term measured out 10 years with bone probes, we achieve about 80% of the normal mandible in terms of PO2. So we are growing new tissue. All right, the drug for disease processes, not the diseases. And essentially, what are we treating? Acute, subacute, and chronic wounds. This is a treatment for wounds in any location and of any duration. That's what hyperbaric oxygen therapy is. Hyperbaric oxygen therapy is not this list of little diagnoses. We have a treatment for wounds in any location and of any duration in the body. Now let's go back. These are all wounding conditions. Every single one. And infections are a type of wound. What do? They induce a tremendous inflammatory reaction, which is part of the wounding process. And once inflammation is started, it's plugging the DVD in. It runs from start to finish, which is scarring and chronic wound healing. And it doesn't matter what the cause is. Focal ischemia, global ischemia, toxin, electricity, any other type of poison, ischemia, low blood flow, low oxygen, etc. So all wound conditions, and we're growing new tissue. So here's the thing. All these years, if you think about it, if the input is a daily intermittent exposure to hyperoxia, and we'll talk about this in a minute, and increased pressure for a chronic wound, wherever in the body, and the output is a reversal of pathophysiology and growth of new tissue, what has got to happen? You've got to go through the DNA of the cell. We have to go through the nucleus somehow, somewhere. You cannot get replication of a cell without getting replication of the DNA, etc. Something has to start the replication process. Turns out, hyperbaric oxygen is a DNA signaling agent. We're promoting DNA transcription of genes. We're expressing hormones, proteins, and we're upregulating receptors. I mean, plus other things. This is just a very short list. And if we look at the average gene with enhancer and, you know, the segments that eventually lead to the gene and the amino acids coding for the protein, somehow hyperbaric oxygen is causing this activator protein and others to now put the key in the lock and begin transcription of the gene sequences and or suppress them. All right, so let's look at this just a little bit different. We know that lack of oxygen triggers all sorts of genes. Hypoxia-inducible factor 1 alpha gets stimulated. That controls 60 genes that are known. And there are a bunch of references on this stuff. So these guys asked in St. Louis, well, why couldn't hyperoxia initiate DNA signaling? Okay. If we've got genes that are sensitive to lack of oxygen, it only makes sense. So what they did was this study with hyperbaric oxygen growth factors. They made rabbit ischemic ear ulcers, and they found that hyperbaric oxygen alone for these ischemic ulcers increased granulation tissue. Growth factors increase granulation tissue more, but when you combine the two, they kick butt. They heal the wounds. And so the two of them appeared to be synergistic. Changes in oxygen partial pressure increases may influence the interaction of growth factors, which we know are acting at the DNA level, and their cellular targets. Growth factor oxygen interaction. Well, beg the question, what's the target? And here's just their data where you see the no ischemia normals are the white, and here's the combined hyperbaric oxygen growth factors, and the others are hyperbaric, just ischemia alone, hyperbarics, and the growth factors. And you can see there's synergy in every one of these experiments they did with different growth factors. This one even had better than the normal healing. So they followed it up and they did another ear model, 1997. And they divided the arterial input at the base of the ear, and they put an oxygen sensor in it. I should put the picture in here. And then they did either a daily exposure to hyperbaric oxygen for 5 days, or 14 days, or they gave them a daily exposure to normal baric oxygen, 2 atmospheres for 90 minutes, and beginning the first post-op day, so they waited 1 day, versus the normal baric oxygen. Well, and the results was, what they found was an increasing room air PO2, and PO2 in response to both normal baric challenge and hyperbarics, with an increasing number of hyperbaric treatments. So our baseline value of oxygen was making a daily increase with each hyperbaric treatment. And they found that there was also a decreasing time of oxygen to return to baseline after the normal baric challenge. So if you gave a challenge of oxygen to the ischemic tissue, oxygen level goes up, but the tissue hangs on to it. It takes a long time for it to decay back. That's not normal. Normal tissue, it goes up, rises, and it drifts back down. But as they treated repetitively, the tissue started acting more normally. Something was happening there. What they found was a prolonged and sustained increase in tissue PO2 was not necessary for successful HBOT. So, you know, the longer you have the hyperbaric oxygen, more oxygen is better. You know, we were all kind of geared on that. That wasn't the answer. In fact, it was a shorter period of time. On the contrary, the duration of tissue PO2 elevation above baseline in response to hyperbaric oxygen exposure decreases as the therapy progresses, and yet the animal is healing. If it was acting as a metabolite alone, the opposite would be true. More oxygen, more better, right? Faster healing. And they even tried some more intensive hyperbaric protocols, twice a day. And then they tried 3 atmospheres. Didn't make a difference. It was the same. And what they said was, this demonstrates a distinct alteration in the physiologic response of ischemic tissue to oxygen following hyperbarics. And it points to a relative increase in blood flow to the ischemic tissue in direct proportion to the cumulative number of HBOT sessions. Well, so baseline PO2 values changed very little though. So it couldn't be due to an arterial input. We weren't changing the input blood supply. We were changing something at the cellular level. and they called it an increased capacitance of ischemic tissue. That was what stimulated the wound healing, and it's relying on oxygen for signal transduction of healing pathways. We know wound healing does. So guess what? The oxygen in hyperbaric oxygen therapy exposure must be acting as a signal transducer. So this is oxygen as a DNA stimulant. I don't know how many of you have seen this paper. It's buried out there, right? 1997, none of us want to look at it. It just got passed up, ho-hum. Really elegant, though, because it goes to what we're talking about. And here is their data. I'm sorry, this comes right off the PDF. It's just a crappy copy. But what it shows is the ischemic gravity with hyperbaric oxygen starts at 32, gets to 95. The ischemic gravity with daily normal baric oxygen only gets up to about 35. In the non-ischemic gravity, we don't change it that much. You can see that, either normal baric or with hyperbaric. But with hyperbaric and ischemia, we are doing something to the cell. Well, here is what is happening as you treat. With every hyperbaric treatment, the amount of time it takes to decay back to baseline, it's 4 hours in ischemic tissue with no hyperbaric treatment. But as you get to about 4 hyperbaric treatments, pretty soon the tissue's not hanging on to oxygen that long. By the time you get out here, you've reached what normal tissue acts like. So you've changed that tissue's response to an oxygen challenge. And here's what happens with 5 treatments and you stop. If you keep measuring it out, they make a little further improvement. But if you keep going day by day, we're inching this thing up. We are continuing to change it with every single hyperbaric treatment. And the answer is that we are affecting something in the nucleus and changing the capacitance of the cell to handle a signal from either growth factors and or oxygen. Well, if you then look over the next 21 years, there are sporadic articles in the literature on individual gene signaling by hyperbaric oxygen. These are just some of them, and you got them on your slides, but growth factor, receptor, platelet-derived growth factor, intracellular adhesion molecule 1, so affecting the inside of the endothelial lining, vascular endothelial growth factor, hypoxia-inducible factor 1 alpha, angiopoietin, another angiogenic protein, mitochondrial DNA transcription and replication. I mean, how much talk have we had about affecting mitochondrial pathology? The apoptotic genes, basic fibroblastic growth factor and fibroblastic replication, procollagen mRNA, heat shock proteins, the antioxidant proteins and mRNA, etc. We've got a lot of evidence. Well, guess what happened? And finally, about 2008, molecular biochemical techniques caught up. And now we have the ability to look at the whole genome, not just selected gene products. Massive gene array analysis, quantitative PCR techniques, and now we've got a series of articles on differential gene expression of 40% oxygen at 1 ATA and 2 ATA air. Godman, regulation of 8,101 genes with a single hyperbaric treatment. Chen, differential gene expression at 1, 2, 4, and 6 ATA of air and oxygen. Kendall, differential gene expression at 1, 1.5, and 2.4 ATA of oxygen. Increasing amounts of this. This is the Godwin one. These are all physiologists that aren't hyperbaric docs. What they did was take vascular endothelial cells, human, biopsy tissue, grind it up, take the cells out, plate them, and exposed them to a single hyperbaric treatment at 2.4 ATA. At the end of 24 hours, 8,101 genes were up or down regulated. And what were the genes we turned on? Dr. Moa showed you some of this literature, as did Dr. Shore. The anti-inflammatory genes, and the genes that code for growth and repair hormones, which are the ones that are stimulating growth of new tissue. And what were the genes that were downregulated? The pro-inflammatory and the apoptotic genes, program cell death. If you gave them a treatment by 48 hours, what happened? And this is happening sequentially over 24 hours. What happened by 48? The cells began to round up and form microtubules in a petri dish. Turns out, Kendall showed that you downregulate multiple inflammatory and apoptotic genes. We upregulate neuroprotective and antioxidant genes, is what the Chen one showed. Well, what have we got here, really? We haven't known this all these years. We can go back to 1662 with first exposure to pressure with Henshaw in England. We really have, and we need to stand up and start touting it. We have the oldest, most enduring, and most effective gene therapy known man in medicine. And I will venture that we will never be able to equal what we're doing with hyperbaric oxygen. something that from a basic biological level, pressure and oxygen can affect so many genes. We're out there trying to do gene therapy with individual genes. Okay, so gear shift again. All right, well, further definition of what we're doing with hyperbaric oxygen. Okay, the congressional appropriation I talked about earlier, where we got $1.2 million. We're trying for $10 million. Shoot high. It's the Air Force, aim high. And we want to do a very large randomized study in veterans. Okay, we got $1.2 million. And so that's when I started that whole questioning to the FDA. Well, hey, is this a significant risk medical device? Do I have to get an investigation on the drug exemption? Nobody does it in hyperbaric medicine historically. Lost application, reapply to the devices section, and then they tell me, nope, you got to be under the drug section. So I submit the whole thing, the protocol, the everything, and this is what I want to do. A single hyperbaric oxygen dose versus a no treatment control group. We're not going to get into all of the multiple control groups and pressurized air, make all the mistakes, I should say. A true control is a control where you omit the active ingredients of the experimental group. Well, that is no treatment, essentially, which is a time control. It allows you to see the natural history of the disease. It is the only really true control. And it was supposed to be multi-center with us in Oklahoma State, and the FDA said, no, this is unacceptable. We consider your intervention, hyperbaric oxygen therapy, to be a combination therapy, the constituents of which are hyperbaric treatment and hyperoxic treatment. Each of these constituents has the potential to contribute independently to the overall therapeutic effect. I said, well, what? Now, mind you, you gotta, in medicine, there's the second opinion phenomena. Or, in residency training programs, every month, the residents rotate, you get a new fresh batch of faces, and they come in and they go over the chart. The beauty of that is it's a fresh look. You now come in, you see a patient, you start adding up everything you're doing. Somebody said, hey, wow, nobody ever took that patient's fever or temperature. He's got a fever. Oh, how'd that get missed? That's a really extreme situation. I'm saying, you find stuff that hasn't been done, you get a fresh look, and that's partly, I think, why I ended up where I am. I was in a surgery program, got hit by a car, and I came into hyperbaric medicine as a complete newbie, unpolluted by even the residency training program that we have, the fellowship in hyperbaric medicine. So I was fortunate enough to not be constrained by the dogmatic thinking. I could look at this in kind of fresh look. But this was like triple fresh look, slap your face 3 times fresh look. And I said, what are you talking about? And this was their fresh look. They're saying, well, wait a minute, you're putting someone in a hyperbaric chamber. You're turning up the pressure and you're turning up the oxygen. You got 2 things going on, pressure and oxygen. I said, okay, all right, then mechanistically, that operationally makes sense. But in my 26 years up to 2012, nowhere, at any time, has there been any discussion or information in any meeting I have ever been to, in every article, any article I have ever read, anything in under HMC and hyperbaric medicine, UBR, you name it, symposia, that talk about the biological activity of pressure. So, when the going gets tough, it's road trip time, right? Well, go to the library. And you aren't going to believe what I found. Did a literature search on the biological effects of pressure. Since the 1940s, there are dozens of articles on physiologic and biological effects of pressure, including micropressure. In 2000, Dr. Murwaugh called me up and said, wow, we just saw the data. He goes, we're having trouble making sense of this. We got the same outcome in our 2 groups here. Are you familiar with it? I said, this was the danger of doing this study 2 years before. We had talked about it at Dr. Newgar's symposium in '99, and I'll never forget because we were sitting up there, we had kind of a panel, and we were talking about, yeah, so would you finally get funding to do what you protocol? And she said, well, yeah, we got to do this control group of 1.3 AT And I go, oh my God, nobody's ever looked at that. I said, you're testing an unknown. And he said, I have no control, we can't change it. The government appointed Colette, he's in charge, we couldn't to do this. And they went forward with the unknown, and they got seemingly unknown. They called and said, well, what do you think? And I said, you know, I've heard the Russians have used some very low pressures, but there's just very little out there about this. We were all a little bit dazed by it. Well, you know, it's part of medicine. The physiologists and the PhDs never talk to the MDs and vice versa. It's an ego issue. I don't know what it is. But just go look in the literature here. Dozens and dozens of articles going back to 1940. And this became the foundation of the letter to the editor that I wrote to the Wolf TBI DOD article in Journal of No Trauma. And as much as they didn't want to, they couldn't deny this. Pressures from 1.21 to 126 ATA delivered to human, and look at that, 0015 to 1.015 ATA to animal endothelial cells, and 1.1 to 1.2 ATA to human platelets. 15 minutes or longer have caused the elaboration or suppression of vasoactive substances, growth factors, inflammatory mediators, oxidation products, and cell proliferation. This literature and biological effects from a 1 minute exposure to 1.09 ATA or 3 minutes at 1.04 inform the symptomatic improvements noted in the Wolf and Associates shampoo, as do benefits of hyperbaric air and spinal function. I don't know if you saw this in veterans with spinal cord injury and PTSD during a scuba diving training course. Let's look at that again. Look at these pressures for 15 minutes or longer. We have bioactivity. And here are the studies. You can look at them going back, you know, and I put Orville Cunningham in there because he talked about this. What did he make his debut with? Spanish flu. In fact, they were going to do animal experiments until they brought him the medical student that was dying of lung involvement from Spanish flu and pressured him to put him in the chamber, and he saved him. All of his work was done with pressurized air. All the work on syphilis and various other conditions. But if you look at these and look at the years and look at all the different models, aortic constriction, vascular, sleeve muscle, kidney cells, this is very interesting. You think about it. This study was done at 30, 60, and 90 millimeters of mercury additional pressure. That's equivalent to what we see in what? Hypertension. And what they're showing is that hypertension, this little bit of pressure, in fact, stimulates proliferation of the endothelial cells, the cells in the wall of the renal arteries. Bingo. Isn't that what we've got in hypertension and kidney disease in humans? It's a pressure problem. So if you look at all these, and you look at air, helium, 95% air, 5% CO2, a lot of studies, you know, here's going up to the modern day, 2011, dorsal root ganglion cells, cerebrovascular injury, etc. This is all in your, you've got all of this, and you can look at it. And you can look at the pressures they use, the controls, and so on. These tables are all in the article, how long they exposed them to. Some were, many of them were days, not all of this stuff applies, but you get the idea. In fact, if you go to the Rocky Intertidal, and any of you taken ecology and looked at, you know, you do it in college, they have you mapping the different organisms that you find within zero tide line. So if you take zero tide line, you go a foot below, 2 feet, 3 feet below. You find different organisms that grow in these different layers. It turns out what they've shown is these marine organisms and animals are sensitive to millimeters to a centimeter of water pressure, hydrostatic pressure. And that may be how they are distributed in the water column. So just an awful lot of information to get you to look at these pressures and the outcomes and how long they did it. It was 15 to 20 minutes for 5 treatments. It was 4 to 10 treatments. And this was a human one. Improved symptoms, EEG, blood flow, vital signs, biochemical parameters, etc. And there's some of the references. So biological activity begins within a minute exposure to 1.09 ATA or within 3 minutes at 1.047. So the minute we start compressing, and this goes to now, can we really do, how can you do a pressure control? My idea, and what I suggested to the DOD, because we couldn't beat them back on not pressurizing in the protocols working section of the meeting in Alexandria, Virginia in December of 2008, all the people in the room were insisting on having pressurized controls. I said, well, look, maybe, why don't we had this mistake made in the Colette CP trial. Don't do it again here. We've got 700,000 injured veterans. dependent on this information, not to mention the millions of Americans with traumatic brain injury, hundreds, maybe worldwide, I don't know, in the figures. But, you know, we should do a no pressure control. That's going to be in the upcoming HOP study that is in press right now. And they found exactly that. Hyperbaric groups did better than the no treatment control. But I thought, well, maybe if we just do a fake little pressurization at the beginning and one at the end, we can get by with it. This suggests we may not be able to. So, you know, all sorts of aquatic animals talked about that. Cells respond through a mechanical process. They talked about this. Go get this article. It is such an eye-opener. They're the ones who summed this up. McDonald and Fraser, and we're a little off it. It's, well, it's in your slides. You got it on there. You can pull it up. But a tremendous amount of literature. And this one here, cyclic pressure changes, where they, you know, went up and down with the pressure. Similarly, stimulants, and I forget the hertz frequency of it, but some of them are fairly fast. So the whole point is, organisms are very sensitive to pressure. And it turns out that micropressure effects, less than or equal to what they used in the Wolf study, have demonstrated all of these effects on organisms from bacteria to humans. Well, you know, we can look at this now in the Chen experiment. What they did was they took rat cortical neurons, 12 to 14 days old, and they used a variety of different exposure pressures. 2, 4, or 6 atmospheres of hyperbaric air. I'm sorry, 1 atmosphere, normobaric air or normobaric oxygen. And then 2, 4, or 6 ATA of air or oxygen. And the same microarray analysis of gene expression. They found that 183 genes were up or down regulated more than 1.5-fold, which they took as a significant effect on gene expression. 17 genes responded regardless of the pressure or the oxygen dose. Turns out more genes were altered in air than oxygen. Hyperbaric air condition, turns out the genes that were turned on were the ion transport, neurotransmitters, signal transduction, growth differentiation genes primarily. Normobaric oxygen had similar genes to the air genes. Hyperbaric, transcription factor regulation, DNA signaling, cytoskeleton effects, signal transduction, growth and differentiation, stress response genes. These are all things that are on the other slides there. And here are the numbers of genes. The types of genes, 2 atmospheres of hyperbaric air, and you can see the genes that are affected. They're actually more affected with air than oxygen, but these genes affected by air are primarily suppressive genes, so you're turning off these genes. Whereas with the oxygen ones, it's mainly upregulation for the genes. And you can see even normobaric oxygen has signaling capacity. Here's more of the same. Normobaric, these are all the oxygen genes. You can see both suppressant and stimulant. And here is just more of the same. The differentially greater than 1.5-fold increase. You can see that the air pressure genes don't so much increase, they suppress gene expression. Whereas the hyperbaric oxygen is more one of upregulation of genes and less turning off of genes. Now, there's some caveats to this. Let me just show you this little Venn diagram where 2 atmospheres hyperbaric air, that circles 4 atmospheres and 6. And you can see the genes turned on just with 6 ATA, excuse me, common with 4 ATA, individually with 8 ATA, the common genes to all 3 pressure exposures, and here are the oxygen ones as well. So pressure essentially downregulates in 80% of the genes, oxygen upregulates over 64% of them. Well, there's a little caveat here, okay? These are all done in vitro. So by the time we're breathing air or oxygen and it gets down to our tissues, you know, it's the trickle down from lungs to finally, in the mitochondria, PO2 is 0 to 1 millimeters of mercury. What they're doing, and the cell is experiencing, 5, 10, who knows, maybe 30, depending. These are now cells exposed directly to this pressure. So in fact, the ratio is about 4 to 1. So really, if we go back and look at these pressures, 2 ATA of oxygen is the equivalent of almost 8 ATA exposure to human being, that amount that's getting to the cells. And we know that it has toxic effects, at least on the lung and brain. But at the cellular level, we're at least signaling. So what it doesn't really look at, except for some of the pressure experiments, is what we're doing down low. with these very lower pressures that we're using and low oxygen levels. So we have to partially qualify this. In addition, nitrogen partial pressures are slightly different, and these in vitro experiments, turns out that in vivo carbon dioxide concentration is about 100 times that they used in some of these experiments. So the gases aren't identical, and there's a little bit of squishiness here, but the idea is consistent with what we know, that we are signaling genes and all the biological effects. So the conclusion is that pressure and/or gas partial pressures have profound effects on cellular homeostasis. More genes apparently are altered in response to the hyperbaric air than the oxygen, but again, we're using these whopping doses. Large percentage of genes suppressed in hyperbaric air, primarily upregulated hyperbaric oxygen, and there's a similarity in the genes, hyperbaric air to hyperbaric oxygen. Well, here's now the experiment by O, where they looked at fibroblasts, and they took either 40% oxygen or 2 ATA air for 2 weeks, and what they're looking at, we got now identical oxygen concentrations. The only difference is the absolute pressure. This goes to the DNA, or the FDA argument. Gene expression, microarray analysis, and PCR. And what they found was after they exposed them, and this is now not the intermittent one, so some of these exposures are days long. It's a little different from what we're doing with hyperbaric oxygen. But again, pressure is at least causing signaling here. They found that after you expose them to either 40% oxygen or 2 ATA for 1 week, cells stop dividing. And more than likely, that's the oxygen effect. But it turns out you have 3-to-1 upregulated to downregulated genes in the hyperbaric air. So now we're showing a little different phenomenon than what they showed in the last experiment. But again, the same phenomenon. We are affecting gene expression. Hyperbaric air upregulated the genes associated with cell adhesion, cytoskeleton, apoptosis, and antibacterial response. And actually, this one also had tumor response. So as it turns out, this doesn't blow up well, but the upregulated genes in gray and black the upregulated genes are the ones in gray and black, and the downregulated ones are the ones in white. And you can see the transport genes are downregulated, upregulated, transcription, cell response, signal transduction, cytoskeleton, and the apoptotic gene. So in this one, they kind of turned on programmed cell death, and adhesion was increased also. What this is suggesting is that, given the varying pressures and oxygen, we are signaling different genes, and the idea is that we want to be playing the symphony of genes with respect to the pathology that we're treating. I mean, I don't want to cause more apoptosis. So it turns out, hyperbaric oxygen, if we keep refining our definition, and we should really say hyperbaric therapy, is the use of greater than atmospheric pressure and oxygen as drugs to treat basic disease processes or pathophysiology, and indirectly their diseases. And we can further recharacterize this as, again, we have the oldest, most enduring, and most effective gene therapy in medicine. And that's what we need to stand up and tout. So, conclusions, and I didn't know how fast this would go or how slow, but we've got plenty of time because our next speaker is trying to handle some things for the conference up in Santa Fe. This treatment, HBOT, and you're going to laugh at this, I just had a manuscript in and it was sent back, and one of the criticisms, I should say manuscript, well, I don't want to identify it, but we sent a manuscript in, and I was told it was unacceptable for me to use this term in the article, hyperbaric oxygen treatment or therapy, because we don't know whether it works or not. I shouldn't be calling it a treatment or therapy. Okay, well, we'll figure something out here. But hyperbaric oxygen is mischaracterized as a treatment for select hopeless diseases. The traditional definition is, I don't know, you can't cut it any other way. It's just non-physiologic. It doesn't tell you anything about what we're doing. It tells you about reimbursement. It's a unique dual-component drug for disease processes that's composed of pressure and hyperoxia, which are varying as we compress the chamber, and even while we're in it, and then, of course, as you're decompressing. And then if you put in an air brake, you are going and doing what? You are altering PO2 right in the midst of it, taking it down for your air brake and bringing it back up. More signal transduction. Ooh, I did that again. L.
Press go back, it says end of slide album.
Press go back? Yeah. Who's the electronics person? You got a job. In fact, call 309. You're going to displace my 15-year-old son also. So one of the primary mechanisms of action is DNA signaling. Dosing, it turns out, depends on manipulating these different combinations of oxygen and pressure. And really, we're in the infancy of this. We are so early on, and everybody wants to talk and think, rotely, everything's at 1.5 HBOT oxygen. But we use the 1.5 HBOT protocol. How did we get on that? How did Neubauer get on it? Dr. Rowan and I were talking about it afterwards. It really was a combination of serendipity and the German literature. What has hyperbaric medicine been? We started out with the introduction of it in two places. The United States military, and in a little bit after that, in the Netherlands. In the Netherlands, they were looking at for dissociating carbon monoxide from carboxyhemoglobin. And of course, carbon monoxide binds to hemoglobin at 220 times the affinity of oxygen. So how do you push it off? You have to mass supply the equation on one side with oxygen. How do you do that? Hyperbaric oxygen. And then they have, well, wait a minute, how about with anaerobic infections? So necrotizing soft tissue infections was the other big thing that Bormann was using it for. Actually, it was gas gangrene formerly. So what we started with clinically in the introduction was with very high pressures, maximal pressures. What did the US Navy do? Wow, oxygen, yeah, this may be good in decompression sickness. And what did they start doing? Well, more is better, always, right? So they started with the maximum amount of oxygen, started doing oxygen tolerance tests. They found out what was tolerated, and the protocols, if you look at it, starting at 3 atmospheres and 2.8, and the air breaks, all of this literature on toxicity going back now decades and decades. And what's happened is, by accident, we have come down from there. And Neubauer's experience, what was it? What got him started? He was treating 2 multiple sclerosis patients who had chronic bone infection, osteomyelitis. So loss of sensation in the foot, typical situation equivalent to diabetic foot wounding. Get an infection, don't know about it until it's been there for a while. By then it's in the bone. And he's treating them at standard doses, and lo and behold, the MS got better. He started looking at this. By then, the Czechs had published their little study in 75. And Neubauer came across the German studies in the late 60s and early 70s in acute severe traumatic brain injury and acute stroke. And what they looked at, they did a dosing study. 1 atmosphere air, 1 atmosphere oxygen, 1.5, and 2 atmospheres. And they found that in acute brain injury, a 15-minute excursion to 2 atmospheres paid a detrimental effect on the biochemistry of the cell and its utilization of glucose. And so next thing you know, they started putting this together, and they started dropping down the pressures. And that's the identical thing that we did, purely by accident with divers in decompression sickness. We had 3 multi-place dives at 8 a.m., 11 a.m., and 2. 8 a.m., 3 p.m., excuse me. The 8 and 3 p.m. dives were 2.4 atmospheres for 90 to 120 minutes, chronic wound healing. The 11 o'clock one was a 2 to 2.5 hour osteomyelitis dive at 2 atmospheres. Well, 8 in the morning, you get there at 7:30, old people, diabetic, they're hobbled. People miss. They show up at 8 o'clock, chamber's going, What do you do, come back at 3? No, you just don't get treated. And of course, me, the newbie, came in and said, well, how much of a difference is there between 2 atmospheres and 2.4 on these protocols? And the answer was nobody knows. So well, why don't we just drop them all down and they take their time? If they're late for one, we've got plenty of space in the chamber. And we did. And what happened was the divers going in the chamber after their table 6s were getting neurological improvement. They weren't getting the weird oxygen toxicity symptoms as you repetitively treated at 2.8 and 2.4 ATA. They started taking longer and they kept getting better. And then we had some of those amazing cases that we put in the book. And we tried 1.5 atmospheres, and how do we do that? We had that diver up in Picayune, Mississippi, who now is demented. And for 23 years he worked for that company. He had been their model employee and their top diver. And now that he's bent and demented, they cut his workers' comp off. and family was disintegrating. He was bankrupt, so he loaded his 2 pistols. And he was heading down to New Orleans. The McDermott Diving Company office was right in downtown. And he was going to kill all of the management people for the offshore group that were on the 3rd floor. And he got intercepted, and these attorneys brought him down to the hospital. That guy who was running the Hyperbaric department of emergency room and dumped him there. They said, do something. I said, what do you mean? I said, well, you treated him last 4 months ago. Just, you find something and treat him. And I got on the phone. I called up Dr. Van Beek, and I said, what do we do with this guy? He says there's nothing in diving medicine, but you can call Dr. Neubauer. And I love telling this story because I had been, again, I'm the new guy, I had been expressly warned multiple times, do not talk with Dr. Neubauer, do not interface with him, it will destroy your career. And I called him up. And I'll never forget, because I'm standing at the nursing station in the emergency room, and the cacophony of the ER and all this stuff, and I'm on the phone with him, and we're having a little argument about this. And I said, well, I got this guy, what would you do? And he said, well, he needs 200 treatments. And I said, that doesn't compute. That's $250,000 in hospital charges. Diving company isn't going to pay for it. I won't be able to treat him here. What's the minimum number to get a permanent, measurable effect? And he said, well, why don't you try 40? I said, well, why 40? And he said, we'll get to the last conclusion. He said, well, over the years, it seems like a good number. Now, that sounds kind of flippant, but he, was able to explore the way upper end and the lower end. People who came for a week. And what he found was people who got in that range of 40 had durability. They called up, they came back, they looked better, and you could measure it. You could see it on imaging, too. And I said, okay, well, we'll try 40. We kind of argued about the dose and the pressure and everything. And that was the start. I said, okay, I'll try your 1.5x. I can't believe that's so short, so shallow. 60 minutes. I'm not going to do 60. I'm doing 90. And then we found out as we overdosed people in about 1995 and got them up there, 65, 70 treatments, these 90-minute treatments of pure oxygen, or close to it, was just too much in chronic brain injury. We started having problems. It was mostly in the carbon monoxide ones. So, we started with 40 treatments. If people got better, what do you do after that? And we kept investigating it, and eventually we got to, I'm going to just add one last little component here, because it really underscores what Pierre Montblanc just showed. We started getting people coming from all over. And of course, the senior member of our group got very nervous. What's the university going to think? What's everybody going to think? We're, doing something that's going to be criticized, etc. And so we put it under an RB. And the RB was to look at sequential 40 treatment blocks. And we could do as many as we want, 1,000. But what happened, and if you look back at it, what's about the average number of treatments we do for diabetic foot wounds? It's about 40. It's in that range. What's the average number, the minimum protocol marks for radiation damaged tissue? It's 40. So we have some evidence, chronic ischemic ulcers in the legs of other cause. And now here it is, hyperbaric oxygen for neurological application. So we started doing blocks of 40, and that's exactly what we found. We got a result with 40, we got more with 80. We got even more after that, but then we started overdosing patients. And in fact, we started looking at a variety of different doses and pressures, and pretty much reaffirms what is here. So when we presented this at UHR's meeting in '94, people said, well, that's just not believable, you don't have an animal model. So the very first animal study we did was 0 versus 40 versus 80 hyperbaric treatments in chronic traumatic brain injury. And what we find, the ones at 80 did better than the ones at 40. It was exactly what we saw clinically, exactly what he has just shown with the CP children. And so that became the recommended dosing. And what we had to do with the veterans and everything else, limited by time, money, urgency, and so on, it wasn't the ideal situation. But that's what we finally looked at, and that's the one that's published in Brain Research. So just a little background on it. The whole point is, there's a whole range below where we've been that really we haven't looked at. And we don't have a good idea. And in fact, people can be sensitive all along this, and what you have to do is watch them very carefully, because as Dr. Montblanc said, It's just like we've experienced now for 25 years. People will show you signs of deterioration. They're not tolerating the dose you're giving them. And tomorrow I'm going to show you this in the Wolf study, the DOD study, and exactly the ingredient that's on there. So you can kind of key into it when you're treating your own patients. So again, I want to end with that right there. This is the oldest, most enduring, and most effective gene therapy known to man. Thank you.
Thank you. We are going to have some Q&A. Would you like to take a seat? On the stage, Doctor. We still want to see you. We're going to have 10-15 minutes Q&A. I'm sure there'll be plenty of questions. And then we're going to have early tea. So, I see the first hand.
Dr. Harch, I assume that those babies that they put in the 2 ATA and then the 4 ATA chamber did not come out blind if you said they were well. So could you comment on this rationing oxygen to babies to keep them from going blind?
Well, sure, I'd be happy to. Actually, the one with the expertise on this and who's probably had the greatest impact is Dr. James. And I believe it's the same doctor who reviewed this micropressure, Dr. McDonald, maybe a different McDonald, but Dr. McDonald postulated that it wasn't the level of oxygen that the babies were getting that was causing retinopathy of prematurity. It was the habituation to oxygen and then the sudden withdrawal of it. And what they showed was that the vessels can go into vasospasm. Well, you've seen the experiment that Dr. Zhang has done in neonatal rats, looking at pressures, and there's one, the Italians, Ricci, did a study on tonic exposure to 1.5 ATA, and didn't see this. So the mythology and dogma is that the oxygen is the problem. However, what we're doing here is an intermittent exposure, and it's an entirely different mechanism. So these babies, as it turns out, what they did, at 2 atmospheres, many of them woke up. They weren't in there for very long. As they described it in the article, they pinked up, they were screaming, and they eventually brought them out. So they didn't get a very long time in the chamber. If they did start breathing in 2 atmospheres, they took it to 4. Well, when they brought the babies out, 1/3 of them, almost all of them, they got something out of, the great majority, but about 1/3 of them regressed. They put those back in and treated again, and they didn't make it. It turns out almost all of those had fatal diseases. You know, atresia of the lungs, major heart malformations, stillborn, diseases incompatible with life. It's the rest of them that survived with the startup. And no, discharge from the hospital apparently well. No, blindness was not mentioned anywhere in there. Now I got to tell you the follow-up to it. There was a lot of criticism over there. What are you doing? I mean, we now have intubation. You didn't intubate them all. You should have kept going with your resuscitation and so on. And they said, what you need is a randomized controlled study. So they did a randomized controlled study, but it was an unequal comparison because the hyperbaric treatment, what they were doing was especially the children that were born after tea time, you know, when the hospitals, the doctors all went home in the evenings, the births, they had no treatment. There was no doctor there, nobody came in, so the children died. So they put them in the chamber. So the randomized controlled experiment was they brought in all of the most skilled pediatricians, resuscitation and intubation and so on. They had them sleeping in the hospital. So they had round the clock, and it was a randomization to either maximum resuscitation with a skilled pediatrician or putting them in the chamber. And it turns out the two had an identical salvage rate. It was in the 15%. See, hyperbaric oxygen didn't work. Right? Now, what would you have done if you had done CPR plus hyperbaric oxygen? The whole point was it was a hands-off resuscitation versus the hands-on. And what happened after the experiment, they wrote the letter back to the, you know, to respond to the letters to the editors and said, we're back where we started now. All the docs went home. They don't sleep in the hospital anymore. We have all the kids dying at night because we can't put them in a chamber. But the point was there was no blindness. That was not even reported. You don't get it with an intermittent exposure. And you now look at all the children that have been treated, Dr. Marois. We've treated, I don't know, almost 400, I believe, with a whole wide range. I don't know, we tallied up 70, 80 different neurological conditions now overall. We haven't seen blindness. Quite the opposite. In fact, they start to see, especially if it's a cortical problem, we get return of vision. So that's more the dogma that we have. No, it's not a problem.
Thank you for that answer. We have a question at the back of the room here.
Hi, Paul. Greg Kitzkin here. Very excellent talk, very good information. I applaud your continued crusade to promote hyperbaric oxygen as a non-pharma drug. It's an uphill battle, and you're a warrior, and I appreciate that. As an unnecessary aside, I might add, I do agree with your brain spect interpretation. My question is, would you comment on, you kind of went over it a little bit, maybe I missed it, the use of 5% carbon dioxide in some of the treatment protocols. Well, what is the rationale behind that?
Well, it was called carbogen. It may still be called carbogen when it was first used. It's a 95% 5% mixture, O2, CO2. And the whole idea is that, as we know, even a little whiff of oxygen from nasal cannula oxygen, all the way up in dose to however many atmospheres you go to, oxygen is vasoconstrictive. And it's the body's protective mechanism to try to combat oxygen toxicity. As it turns out, that effect on vessels is a fraction of the effect that CO2 has. So for a 4 millimeter change, even 2 millimeter change in carbon dioxide level, the amount of vasodilatation is much greater than the proportionate vasoconstriction you get with oxygen. So the idea was, if we're going to give oxygen, we get some mild vasoconstriction, why don't we give a CO2-rich mixture that will overpower that vasoconstrictive effect and vasodilate? And that was done. And what happened was it accelerated oxygen toxicity in the experiments, especially with animals, but the same thing when you do with humans. So if you do use that with the idea of trying to deliver a higher dose of oxygen, what we're seeing is that, how much do you need for signaling? We may be doing a lot of overkill here, especially with even what we're doing in divers. Maybe manual and in other experiments, they've shown that 2 atmospheres of oxygen, really that's the maximum benefit. All the 2.8 ATA, you may not get much more out of it, if at all. So 5% CO2, you're going to have to make sure you use an air brake. And using 5% CO2 with anything that's going to increase oxygen content is, you got to be careful.
Thank you for that question. Here's our next question here.
Yes, doctor. On these prescriptions where you've got 40, 60, 80 dives, how are you mediating the hyperbaric-induced myopia? Or how do you address that in protocol?
We just tell them up front, the hyperoxic myopia?
Yeah.
We just tell them. In general, it's a dose-response phenomenon. And at the lower doses, we don't see it very often. It does happen, but usually when we see it, it's in older people. So people who have had, we just had it occur with a person, and she's 69, and I should call her competition fisherman. But she spent a ton of time outdoors on the water, incredibly UV exposure. And she's having some hyperoxic myopia with an intermittent exposure. I think she's at 1.35 ATA for just 15 minutes. So I'm just upfront with people and I tell them, if I'm treating you for a foot wound at 2.4 ATA at standard 90, 120 minute protocols, I said it's going to be almost a guarantee. By the time you get to 30 or 40 treatments, you're going to have some hyperoxic myopia. Or I should say there's a substantial chance of it. Most of the literature shows that the majority of that is reversible. But they're now measuring out, even a year's time, that you can still have some residual effects of it. Now that's with people with totally normal eyes. In fact, you get people who've got abnormal eyes and wear glasses, I tell them, hey, it's a roll of the dice. This may alter your refractive index, and we've had people, they get an improvement in vision. Stop wearing the glasses, but they don't need it quite as much. So I tell them it's dose response, and if we're at the low doses, we're likely not going to see it. We usually don't see it in the children, but it's a potential risk.
Thank you.
Just inform them.
We have a few more questions, Steve.
You said that for the preemies that were put in oxygen tent, the oxygen partial pressure was
Oxygen
about,
chamber,
or,
hyperbaric chamber.
okay. but
Oh, you're
the
talking
ones
about.
where right now, the
Okay.
fireplace comes into play, the oxygen partial pressure is about half an atmosphere. Did I hear that correctly?
No, I have to go back and look at it. No, they were giving these kids as much as they needed to maintain PO2 for their lungs.
Okay.
So usually it was preemies, premature lungs, and hyaline membrane disease where you can't oxygenate. So they're given as much as they need. I remember seeing some of the stuff at 80% O2.
The reason I'm asking is, from my set padding days, the long-term, the PO2 limit to avoid long-term oxygen toxicity, which is basically painful breathing, in normal adult humans is about 0.4 of an atmosphere.
In SAT, but it's a time dose phenomenon.
True, and it starts at about 24 hours.
Right.
And then putting these kids at 50 to 80, or 0.5 to 0.8% for many days?
Yes. Actually, we got to back off. The SAT pressure is 0.3 to 0.4, 0.5 ATA. You can go for a long period of time, actually. That's the tolerance level. But yeah, you go much above that and the time shortens. You can't tolerate it. And the babies are it's as much as you need to oxygenate the blood.
Thank you.
Oh, and let me add one more thing. What Phil James also documented in the stuff that McDonald had published it was in some publication, I forget, but what they did was they took the neonates and instead of doing an abrupt cessation, they weaned them off the oxygen. And what they found was they didn't get retinopathy prematurely, and they also did not develop CP, brain bleeds, and so on.
A lot of preparation work goes into this. That was the second of 3 individual lectures. A lot of time and energy. Can we all show our great appreciation to